quite straightforward. It's just the complement of an open set. So we already have the big set for which the topological space is defined, and we have members of the topological space that are the open sets, and we just take their complement, and there you go. That's a closed set. And yeah, the book lists some examples, and people who are experienced with metric topologies will be very familiar with them. So notable ones include closed interval AB in an order topology. So that's easily seen. And in the product topology R2, we can also have a product of, let's see. So how is it defined? Yeah, it defined it as the first half of the plane, including the boundary. That's one way of doing it, but note that this also happens to be a closed set in the usual sense because essentially it's a complement, cross a complement, and then the whole thing just comes out. Another way of saying it is that the part other than this interior, not including the boundary, is an open set, right? That's because it's a union of a couple of open sets, right? So that's one way to visualize it. And yeah, box is a closed set. Anything else? Yeah, in the finite complement topology, all finite sets are closed. We're going to get to Hausdorff soon enough. In the discrete topology, every set is open and closed. So yeah, because it's the power set of X, so the complement is also yeah, it's both. So that's what clopen means. It's closed and open. So in the discrete topology, every set is clopen. That's what it means. But so note that this set, which I was incorrectly calling clopen for the sake of convenience, is not actually closed. It's neither. So yeah, you have examples of all categories of sets. You can have only open sets, only closed sets, both and neither. So yeah. Okay. I'm not proving it, but essentially phi and x are closed because phi is open. So x is closed because of x minus phi, and x is closed because of x minus phi, and phi is open. So yeah. Now, and by De Morgan's laws, you can prove the other union and intersection thing. So essentially, because of De Morgan's law, the complement flips the union and intersections. And one benefit of starting with open sets instead of closed sets is that you can define basis very early. The basis, by the definition, since it has to be contained in P and so like that, you can't really have a basis of closed element, at least not to my knowledge. So because like in some interesting spaces, a single point set, many interesting spaces, a single point set is closed, and you can't really get an interesting basis out of it. So that's one reason to start with the closed set. But here we're going to discuss limit points anyway, so you can start with closed sets, discuss limit points, get to open sets, discuss it. So yeah, no particular advantage. I do agree with that. Some people just start with both at the same time. Okay. Now, yeah, first major theorem. Let's see. So this one is used in the architecture, and then you prove major theorems about closed spaces. But the most useful theorem of this chapter is probably theorem 17.5. So we'll get there. A is closed in Y. So you have a subspace. Yeah. Yeah. A is closed in Y if and only if A is equal to C intersection Y and C is closed in X. Okay. So it's quite straightforward. You just mess around with the complements and then define what the closed set C you want it to be. So let's prove this direction first. Let's see. So A is closed in Y. So A is equal to Y minus W. W is open in Y. And W therefore is equal to V intersection Y, and V is open in X, right? Okay. We're almost there. Just let's see. Let's see. Okay. So this is open in X. So X minus V is going to be closed in X, right? By definition. Okay. intersection y, what is this equal to? Let's see. This is equal to y minus w, right? And this is equal to c intersection y. So our c is x minus v, and our y minus w is a. So one direction is done, right? Yeah. Okay. Now for the other direction, let's see. So A is equal to C intersection Y, and C is equal to X minus U, right? Okay. So let's just break it down. We get Y minus U intersection Y, and this is open in Y, and this implies that A is closed in Y because it's a complement of an open set in the subspace topology. So yeah, the proof is quite straightforward. It's just an application of the definition of the complements, just set theoretic manipulations. Yeah, and I'll prove 17.3 here, that too. Let's do it. Okay, so Y is a subspace of X, A is closed in Y, and Y is closed in X. Okay, then A is closed. Yeah, that's pretty simple. So A is equal to C intersection Y by previous theorem, and Y is closed, C is closed in X, mind you. So A is therefore the intersection of two closed sets, and by theorem 17.1, it's closed in X. So yeah, quite straightforward. Okay. The interior, so there were, in the metric space, you may have seen another definition first. So you'll see the collection of all interior points, and that's what we're going to prove later, is what the interior of A is, right? And for the closure, we define it as the A and all limit points in metric. Here, so essentially you can prove that both the definitions are equivalent. In fact, that's what 17.4 is. So one definition is the intersection of all closed sets. Um, C, A, and C is closed. And the point is, because it's the intersection, we know that A closure is the smallest closed set that contains A, right? Because it's intersection, so by definition. In metric spaces, you have to prove it from the other definition. Here we don't have to because again we have the equivalent. So if you show that two sets are equivalent, then you don't have to do much, right? Yeah. And same thing with the union. So it's the union of all the open sets in A, I think. Yeah. But that U is contained in A. So that's why you get that the interior is the biggest set that's contained in it, right? It's the union. So any set that is contained in it that's open is going to be in there, and therefore the union is going to contain, and the intersection is going to be contained in it. So yeah. Now closed, yeah, that thing, yeah. And it's clear that if it were to be closed, then they would be equal because, well, A is a set that contains A and is closed. So it would be here, and you can prove both. So A closure is always trivially a superset of A, and interior of A is always trivially a subset of A by this criteria, essentially. So essentially, if you take an arbitrary union this way, then the this thing, the inclusion remains. We've done this before. So yeah. Okay, let's prove the theorem now. Okay, so mhm, mhm. Okay, so let B be the closure of A in Y. So yeah, hmm. Okay. So we have to show that B is contained in A closure intersection Y and vice versa, right? So that's if we show that, then yeah. All right. Now this is where theorem 17.2 comes in, and essentially, yeah, once you show the equivalence of the intersection definition and the limit point definition, then you just forget about theorem 17.2. But right now you need it. So yeah, let's see. So B is, sorry, just let me check. A is the closure of A and X. Yeah. So A bar contains A and is a closed set, right? Okay. Yeah. So A bar intersection Y is going to contain A intersection Y. Just, set theoretical. So what does this mean? Yeah, observe that this is going to be a closed set in Y by theorem 17, right? So this means whatever B is, it must be contained in it by definition, since it's the intersection of all those sets. So B is contained in A bar intersection Y. That's how you prove one direction. Now for the other one, let's see. So B is a closed set. No, that's it's, oh yeah, I just wrote it twice. Yeah. Okay. So B contains, yeah. Okay. So we have to go backwards essentially. So B contains A intersection Y, and B is closed, right? By definition. Now what? Now, yeah. So B is a closed set in Y, right? So that means B is equal to C, which is a closed set in X intersection Y, right? Some set exists. Okay. Now, yeah. And this contains A intersection Y, right? So what does this mean? That means C intersection Y is going to contain A. Oh, sorry. So can we go backwards here? Is my question. Let's see. We can go backwards here. Yeah, we have no problem going backwards here. So what we get is C is a closed set in X now from the theorem that contains A. And that means by definition, C is containing a closure. And that means now we intersect, now we go back. So C intersection Y contains A closure intersection Y. And that means B contains A closure intersection. So yeah, we proved both sides. And we can forget about theorem 17.2 now. Essentially, just need it when concerning about the hardware of subspace topologies with closed sets. And now that we've proven two major theorems, we can use them directly, and we almost never need the smaller weaker. Yeah. Okay. Yeah. So this is the major theorem, 17.5, because yeah, essentially you can also use this theorem to check whether a set is, because if it is closed, then it's going to belong to by just belonging to, and then you can use the theorem. So yeah. So keep in mind all things are subsets of X, and that's precisely why we can use complements in the proof. So X belongs to a closure if and only if there exists, hang on, yeah, for all U of X, and I'm going to write it this way because instead of whatever the hell the book says, because this is far easier, and I do not want to write the word neighborhood every single time, or even NH, whatever. I do not want to write it. I will write U of X, because U, V, and W typically represent open sets. So yeah, so U of X is it is okay. So yeah, for all U of X, neighborhoods of X, U intersection A is What? Not empty? Is that it? Yeah, that's essentially what it means. So that's what it means for you to intersect. Yeah. And that's if and only if for all basis elements of X, uh, B intersection A is all basis elements containing X, B intersection A is not fine. Yeah. And I'm just going to flip this around and make it the negation. So we have to mess with the quantifiers again. Yeah. So these two are very easy to prove to be equivalent. This is the main challenge. And we've already have the work from changing it to their negation because now we have an existential one. So yeah. Okay. So if X, let's prove this direction first. If X does not belongs to a closure, that means by definition there exists a C that contains A that is closed such that X does not belong to C, right? There has to be something. You can take A closure itself, but why, right? Now, from this C, yeah, X minus C, so observe that it goes backwards too. The complement of a closed set is open. So this can be called U, and it's going to be open, and it's going to contain X with the neighborhood of X. And since C is containing A, and we're flipping it, U intersection A is going to be phi. You can check it set theory again. So what does that mean? That means if X is, what did I just do? Yeah, yeah, yeah. So we proved this side. Now for the other one, I'm going to, oh, okay. Yeah. For the other direction, let's see. If there exists a neighborhood of X, yeah, actually it's quite simple. So X minus U is a closed set that contains not X and it contains it, right? Because if U doesn't contain a single member of A and we take its complement and X definitely contains A, its complement is going to completely contain it. You can work around it. Yeah. So what does that mean? That means essentially X minus U intersection A is equal to A, something like that. And this works out because of this. So the sum distributive property. But yeah, the point is we've gotten a closed set that contains A that doesn't contain X. So that means X is not in this because it has to be intersected, right? So yeah. Now we just have to show this equivalence, right? Hang on. Yeah. Okay, that's pretty simple. We just have to use the definition of the basis elements again. So note that the basis elements are themselves open, so we're done in this direction. And for the other one, for all X belonging to an open set U, we have a basis element. So we just use that basis element and then we're done, right? Since U is B is contained in U, then B intersection A also has to be phi if U intersection A is phi. Also, so yeah, to get a feel of these theoretic ideas, we'll have to practice a bit, but yeah, that's what the entirety of section one was for. So attempt it. Yeah. Yeah. Okay. Okay. So any examples, anything significant? No, I'm going to skip that one. Okay. So for the 1 by n belongs to z plus 1, for example, this is similar to the that argument. I used it for Rn. So I use that there cannot be in a single open set that contains 0, comma 1. that in the standard coding, right? So it's a similar argument, but in the reverse direction. Every neighborhood of 0 you take, it must contain something. So yeah. Okay. Okay. Limit points. Yeah. So yeah, it's a pretty simple definition, and let's write it down. So if every neighborhood of X has intersects A in a point not other than X, then yeah, then X is a limit point. Okay. So this is denoted as set of limit points. So yeah, that's the definition. Definitions are typically epinemius. So yeah. Okay. Now any major theorem? Yeah. So theorem 17.6 is essentially acknowledging the equivalence of the different definitions of closures. So yeah. Okay. So let's prove it. Hang on. Yeah, I've written the definition. Anything else? No. Yeah. A equals a union A. Yeah. Okay. So note that A is trivially contained in A bar. So we've done in one way. And we just have to show that A prime. Okay. So let X belongs to A prime. So currently we're solving this one. Yeah. If A is a limit point, then for all neighborhoods of X is so hmm, X belongs to 1 and X does not belongs to A implies X belongs to limit point of A. Yeah, by definition, right? Okay. So for all neighborhoods of X, U intersection A is what? It's not contained in X. Yeah. So what does that mean? That means it's non-empty, right? And since every neighborhood of A is X is intersecting A, since it's not contained here, so it's going to essentially. Hang on. Oh wait, I messed up. Yeah, the definition was the opposite. Sorry. Yeah, that was the definition. So sorry about that. Yeah. So given that it's containing X, it's not empty. So because of that, it's yeah, it is going to belong to A closure. In fact, it's going to belong to A closure even with this definition because it's going to equal X. So yeah. So that's one containment, and yeah. So I was tempted to write the other inclusion by A not belonging to A prime, so we can A closure that also can be made into a proof, but let's just follow this. So X belongs to A. In fact, actually, we already did that. X belongs to A closure. Again, if X belongs to A, then we're done. So let X not belong to A. Now what? Now, since X belongs to A closure for all neighborhoods of X, uh, U intersection A is what? Non-empty, right? And let's see. So X is not an A, right? Since X is not an A, it cannot intersect A in X, right? By definition, since A is X is not an A, it cannot lie in the intersection. So actually, yeah, what am I writing? That's actually wrong. This is also wrong. Sorry. Um, this is the only valid definition. Even the containment one is wrong because I think I'm not sure now. You think? Yeah, I think even that containment one is wrong because A need not have X. Yeah, that definition is wrong. This is the only valid definition. Okay, so this is not empty because well X is not even in here, and it must not be empty by the here by this by theorem 17.5. So what does that give? That gives us that it has to be a point other than X, and by definition that implies that X is a limit point. So yeah. So if X doesn't belong here, it must belong here from belonging here. So that proves the other implication or containment, however you want to look at it. Okay. We might actually be close to making it all in one take then. That's cool. Okay. It's closed in only, yeah, it contains all limit points. It's a trivial corollary. So this is trivially true. So if it, so if A is closed, then A is equal to this. So that means A contains A union A prime, and that's only possible when, well, A prime is contained in A. So that. Okay, Hausdorff spaces. So yeah, I'll just discuss the example. So C is a limit point. Is it a limit point? Sorry. Yeah. The sequence xn equals to B converges to C because for all neighborhoods of C, it contains a point B. So yeah, due to this anomaly, it converts. It actually the definition matches perfectly. It actually converges to the point C and A and B. So yeah. Okay. So Hausdorff is essentially you take 2 points that are not equal to each other. There always exists a disjoint neighborhood. Disjoint. So yeah. So every finite point. Okay. So to show that a singleton in a Hausdorff space is closed, we simply have to show that x minus singleton x is open, right? Or if and to show that actually yeah, I'm essentially using 17.5 here again. So if I show that it's an interior point, so the interior point is precisely that there exists a u of x such that u intersection A is so instead of A, we're taking x minus u essentially. No, not even that. We're taking yeah. Uh, so an interior point is essentially you take a point and then there's a open set that's contained in the big open set and yeah, that's basically it in the metric space. So you can see it kind of lines up here and but yeah, we're not discussing metric spaces yet, so I'll avoid all that. So yeah, if I use this, um, if I show this essentially, then I can show that the complement of x is has to be open because this is equal to its closure essentially. So if I show that this closure is equal to singleton x, we're done. And that's how what I meant when I said that theorem can be used to show that a set is closed. Okay. So let y not equals to x. So that means y is belonging to 2, right? Okay. Now, yeah. So y had the Hausdorff axiom. There exists ux and uy such that ux intersection uy is phi, right? And y is belonging to u and x is belonging to ux, essentially. Yeah. Now, because singleton x is a subset of ux by definition, uy intersection u singleton x is phi, and that's precisely what we want. since the set A to be worried about here is singleton X. So what do we get now? We get that, yeah, singleton X is equal to singleton X closure, right? Yeah. Yeah. Is that it? Yeah, that's it. Okay, yeah. I'll just go over it. So essentially, something belongs to its closure. So yeah, I just showed that any that is not equal to X will not belong to X, singleton X closure. So yeah, uh, I just mentioned a lot of extra things that can be perspectives to look at theorem 17.5, and that's why it's the most important theorem of this chapter and clock flow sets. Yeah, and since a singleton X is closed, finite unions of singletons are closed, and therefore finite what? Let's see, finite point set. I forgot the term point set, but not singleton. So that's cool. Yeah. So if the finite point sets are closed, that alone is called the T1 axiom. I think, yeah, I don't know what T0 is. There is something about T0, but like we'll know what the T0 axiom is when concerning regularity, I think, maybe. And that would be chapter 4. Anyways, yeah. Yes. Okay. So with the T1 axiom, we also get that every limit point must contain infinitely many points. So that's to give you an idea in a Hausdorff space or a metric space, just take any point and then you have another point and we have another neighborhood, right? Well, now we have this smaller neighborhood, right? So I'll just take this one for reference. We take this point, we take this smaller neighborhood, we take this point, take this smaller neighborhood, take this point. You can go infinitely, is the point. So that's the idea for Hausdorff space. But proving it for a T1 axiom requires a little bit of a trick. So yeah, note that okay. So first of all, take any arbitrary union of open set of X, so neighborhood of X. So fix it. So whenever we have a for all thing, we need an arbitrary open set. So we just use fix, right? Just get it over with, and then we'll work with that, and make sure it's arbitrary so that the proof lines up. Okay. So now what? Yeah. So U has what? So contains X and till Xn, right? So X1 and till Xn. It has finitely many points. So the neighborhood contains finitely many points of, yeah, okay, what am I proving here? Let's just get that clear. So if, okay, I'm cheating. Mm-hmm, mm-hmm, yeah. Okay, yeah. So X minus all the sets. So yeah, I'm assuming negative with negative, right? So if every neighborhood of X contains finitely many points of A, that's the negation, essentially, right? Sorry, no, there exists a neighborhood of X such that it contains finitely many points. That's the negation, right? And this implies that X does not belong to X is not a limit point of it. So that's what I'm proving first, right? Yeah. And then we'll show that for all neighborhoods of X, if it intersects with infinitely many points, then that implies X is a limit point of it, not. Yeah. And from that, we'll get the FN only. Yeah. So that's the actual proof. Yeah. Now, U of X, It's, let's say this neighborhood is intersecting finitely many points. So these are all the finite points. You can all list finite points. Now, by definition, this is a closed set since it's following the T1 axiom, and therefore this is an open set. And since U is an open set, this is an open set, their intersection is an open set. And this intersection, well, this intersection contains no point of A, right? So since these are all the points of A, it was containing. So what does that mean? That means we've gotten an open set of X that contains no point of A, and by definition, that means it's not even in the closure of A. And if it's not in the closure of A, it's not in the limit. Yeah. Did I get it right? I'll just check. Yeah, not at all. That's the same thing. Okay, now for this one, if it so note that it must intersected in infinitely many points. If it's finite, then you could just have every neighborhood intersected at exactly one point, and that one point could be X itself. So it cannot be finite. It has to be infinite. Or you say at least 3 points or something. Will that work? No, even that might work. There can be problems. In fact, yeah, there you go. These are the problems. So yeah, it must be infinite points. And from that, because there are infinite points and finite point sets are closed, you essentially must, it must be in a point other than A. Hang on, why is that? I'll try to clarify it for myself now, guys. Let's see. So neighborhood of X, yeah, infinitely many points. Yeah, actually, yeah, just not one is enough. So three is enough. Sorry. So if it's infinite, then it has to be a point other than X itself. Otherwise, what does infinite even mean? Yeah. Okay. Last theorem. I'll prove 17.11 with the exercises. Okay. Then a sequence of points converges at most one point of X. So we are using T1 as well here, and that's what people would not immediately realize was the trick. So let's say a sequence converges to X. Is it written this way? Convergence. Okay, it's not written this way, and for probably a good reason, but I'm writing it anyways. So X contains infinitely many points, all but finitely many points of Xn because it has to contain infinitely many points of a closed set here, right? It's not a closed set, but yeah, because it's a limit point essentially. And this is a sequence, so you can enumerate them and all that. Okay. Now y is not equal to X, and by the Hausdorff axiom, there exists a Uy and Ux such that they're separate, disjoint, and therefore, if Ui were to have infinitely many points of Xn, which is the only way it can be a limit point, and it has to be a limit point, like a limit point is a necessary condition for it to be a point of convergence. You can check that. If it also had infinitely many points, then there has to be something that's in their intersection. Why is that? Let's see. Okay, yeah, so they're disjoint, right? If both of them have infinitely many points, then yeah, my bad. X minus ux is finite, or at least this intersected with xn. This is finite, right? And this is containing ui. So yeah, it's a direct contradiction, and that's yeah. Okay, I actually did it in all in one take. I'm very happy about that. And yeah, I'll do the exercises tomorrow, so you might get this video as well one day later. And yeah, I am very happy I did it all in one take. See ya.